Greetings grade 12s and welcome to Butu Academy, Lessons That Empower. We are back again with the second lesson on work, energy and power. You'd remember last time we introduced you to this lesson, to this topic with lesson 1, where we introduced you to the calculation of work done. We are back again with the second lesson. Now today what we're going to be looking at is what is referred to as the work-energy theorem. Now before we go into the slides, let us refer to our exam guideline. Remember, once again, we are still using the 2021 grade 12 physical sciences exam guidelines. Okay, if you look at page 10, just towards the bottom of page 10, what you will see is the work, energy and power topic, and today we are looking at the work energy theorem. You would remember with lesson 1 we've already covered the definition of work done. We've also did some calculations using this formula, and we also introduced you to the concept of net work. Of course, the concept of free body diagrams was covered in Newton's laws and applications of Newton's laws. We also did a differentiation between positive and negative work. That this was all covered in the first lesson. Okay, now in this lesson what we are going to be looking at is the second part of this section, and that is the work energy theorem. And as you can see there, what I've highlighted is the definition of the work energy theorem, which is defined as the work done on an object by the net force is equal to the change in the object's kinetic energy. Don't worry, we're also going to look at this in the next slide. All right, and then there's a mathematical interpretation there as well. After you've defined the work energy theorem and you know the formula, the mathematical formula for calculating the work, the net work, we then move to the application. As you can see in this bullet point here, we will be applying the work energy theorem in various problems and questions. Okay, now let us look at I've just copied and pasted the definition of the work energy theorem from the exam guideline here. The work done on an object by a net force is equal to the change in the object's kinetic energy. What I'm interested in is this part, which is the mathematical interpretation of the theorem. Okay, what it says is that the net work, which is the work done by the net force, is equal to the object's change in kinetic energy. We know about the kinetic energy from previous grade. Okay, so when we can then further simplify this by saying this is equals to we know that delta EK means EK final minus EK initial. We know what EK final means, the final kinetic energy, and EK initial means the kinetic energy at the beginning, or the initial kinetic energy. Okay, we can even further simplify it by saying we know that the kinetic energy is calculated using the formula half mv squared. In this case, because this is EKF, this will be half mvf squared minus half mvi squared. Okay, now the simplification of this theorem, especially in the mathematical format, opens a door for us to calculating various quantities in physics. Okay, so there will be times where you are required to use the work energy theorem to calculate the final velocity or the initial velocity. Sometimes you might be required to calculate one of the forces that are doing work on the object. So there are many calculations that you can do from this particular theorem, although it is only defined with one sentence and also with one formula, but there are many applications of this particular theorem. Let's look at a worked example. In this worked example, we have a situation where a 50 kilogram mass block is moved from rest. Now you remember that this statement, or that word there, means something to us as physical sciences learners. It means the initial velocity is equals to 0. This object is starting with an initial velocity of 0. The block accelerates until it reaches a final velocity of 2,8 meters per second. Therefore, this would be your final velocity. That will be your initial velocity over there. So you have the two velocities given to you from the statement. Okay, then you also have the mass of the object. What are we required to calculate? We are required to calculate the net work. We know the net work is W net, which is what we were doing just now in the work energy theorem. Okay, now in terms of what you should do in a situation like this one, you are required to calculate the net work. You are then going to use the work energy theorem and the information that has been given to you. We know the work energy theorem says W net is equals to delta EK. Of course, there are those who prefer writing W net is equals to delta K. Capital letter K is also used to represent the kinetic energy. Okay, so when we then simplify, this means this is equals to half mvf squared minus half mvi squared. Okay, we then go and substitute. In our substitution, this would be 1 over 2 into the mass has been given to us as 50 kilograms from the statement there. Okay, so then we say 50 VF. Okay, we substitute VF because it's given to us as 2,8 minus 1 over 2 into 50. You'd see that this is actually equals to 0 this side, but let's just substitute anyway. 0 squared. Remember to square the velocities there. We know that this part here is going to be 0, so the calculation is definitely going to be concentrated on this side. Okay, so we then go and check the calculator and see what the answer would be. Now if we, okay, here's our calculator there. Oh, it's blocking my face. Here's the calculator. Let's put it on the right, on the left hand side. Okay, so now we know that this part is going to be equals to 0. That would be the half. That would be the part that uses VI. We know that VI is equals to 0, so we don't really have to worry much about that. Now we are then going to say, okay, 1 over 2, which is 0,5, multiplied by 50, multiplied by 2,8 squared. Remember, we only square the 2,8. We don't square everything on the formula there. Okay, we only square the velocity in the calculation for the kinetic energy. Now in this case, our answer will be 196. So the answer is 196 joules, and that is one of the ways you can apply the work energy theorem to calculate W net. Okay, if you have the two velocities, that would be the initial velocity of the object and the final velocity of the object. Also, you need the mass, because to calculate the kinetic energy you need the mass, hence the formula is half mv squared. Okay, now we then move to another application in this activity, which is going to be the last activity that we're doing in today's lesson, because today's lesson is basically about just introducing you to the work energy theorem and then applying the work energy theorem as you saw according to the exam guideline. That is what is required of us. In this activity, you have a 7 kilogram block which is pulled from rest. Again, the word rest, we know what it means. It means the initial velocity of the object would have been 0, and it's pulled across a rough surface. Of course, the word rough, it means here there is a frictional force that is also playing or acting on the object. Okay, so it's pulled to the right, or from rest across a rough surface by a 120 newtons force acting to the right. Okay, there's the word force missing there. The block accelerates to the right until it reaches a final velocity, or a velocity of 3,2 meters per second. So we have two velocities here again. The initial velocity, as we saw here, rest means the initial velocity is equals to 0 there, and then we also have the final velocity, which is 3,2 meters per second. All right, so we have the two velocities that are required in the calculation of change in kinetic energy. The displacement of the block is 5 meters. Okay, the block is moving to the right, so we expect that the displacement is to the right. what is required of us? The first question says, calculate the net work done on the block for the duration of its motion. Okay, again, we are going to use the work energy theorem here because we have the two velocities and we also have the mass of the block. So we are going to say W net, as we did previously, is equals to delta EK. Right, we know that delta EK is equals to half mvf squared minus half mvi squared. Now let's do our substitutions. In our substitutions, then what then comes would be 1 over 2 into the mass, which is 7, into vf, which is 3,2 squared, minus 1 over 2 into the mass, which is 7, multiplied by 0. Again, this will give us 0. The last term on the right hand side is going to give us 0. But it is good practice to substitute, especially when you are not sure. So we are then going to use the calculator again to calculate the... This is a question that is quite similar to the previous one that we did. Okay, again, now what are we going to do here? We are then going to say 0,5, which is 1 over 2 into 7 into 3,2. We then square the 3,2. Please remember that it's a very common mistake that we see on learner scripts where they square the whole thing or they forget to square altogether. Please remember to square. It's just going to say minus 0. We know that this side is equals, it's negative 0. Okay, let me bring back the calculator here. Okay, let's have our calculator back. Okay, the right hand side of our equation, as we can see there, is going to give us 0 because this is half times 7 times 0. So the last part of the term is not necessary for us. 0,5 times 7 times 3,2 squared will then give us 35,84 joules, and that is the answer for the net work done on the object. That is when we use the work energy theorem. Okay, now the second question says calculate the frictional force acting on the block. Remember, we were told that this is pulled across a rough surface, so there's definitely a frictional force there. We are calculating the frictional force. Okay, let me just remove that answer there. It was 35,84 joules, just so that we can all see. Calculate the frictional force acting on the block. Now, in this case, we already know what W net is equals to. Remember, W net is the net work done by all the forces acting on the object. One of the forces acting on the object is the applied force, which is 120 newtons, which is acting to the right. And since the object is also moving to the right, it means our frictional force, which is brought about by the rough surface here, will be moving to the left. So we have those two forces that are acting on the object in opposite directions. So we now know also that W net is also equals to the work done by the applied force plus the work done by the frictional force. If we go ahead and simplify the work done by the applied force will be the applied force multiplied by delta x multiplied by cos theta, plus the work done by the frictional force will be the frictional force multiplied by delta x multiplied by cos theta. Okay, in our substitution, remember W net, we already know what it is equal to. The value of the W net was calculated in the previous question as 35,84. This will be equals to 120 times delta x is given to us as 5 there, times 5 times cos. Now you have to think, don't just rush into substituting the theta. They have to think about remember, theta is the angle between this force and that delta x. Both of them, according to the statement, are to the right. The object accelerates to the right. The applied force is also acting to the right. So the two are in the same direction. Therefore, the angle between them is 0 degrees. plus we don't know what the frictional force is equals to. So we just substitute it, multiply by 5, which is delta x, multiply by cos. Now you have to think about theta again. Remember, the object is accelerating to the right, and we know that the frictional force must always oppose the direction of motion, which means the frictional force is to the left. If the frictional force is to the left, the angle between the frictional force and the displacement, the angle between this frictional force and that displacement there must be 180 degrees. Okay, so what do we get? We then in our simplification, this will remain 35,84 on the other side. Let's then calculate what the right hand side is equals to. Let's go to the calculator and find out what those values are. Okay, now 120 multiply by 5 multiply by cos 0. We know cos 0 is equals to 1 anyway. We get 600. Okay, and then this means this 35,84 is equals to 600 minus, we know that 5 multiplied by cos 180 will be negative 5. Okay, so that's why we say minus 5f. What do we want? We want f. Okay, we transpose the 600 to the left hand side. If we do that, we then get let's calculator. The 600 will be negative. When it goes to the other side, it becomes a negative 600. Okay, so this would be negative 600 plus 35,84. Of course, you could have just said 600 minus 35,84. It's still the same thing, but the sign is negative there. So that's negative 600 plus 35,84, which then gives us negative 564. So basically negative 564. Okay, let me just quickly check what was the decimal places. 0.16. Okay, 0.16 is equals to negative 5f. Okay, just make some space this side. Obviously, to get f, we have to divide both sides by negative 5. The frictional force therefore will be equals to the left hand side divide by 5. Okay, so we're going to then divide the 564,16 divided by 5. Then we get the answer to be 112, comma, okay, again I forgot to check the decimal places there. Okay, comma 83 or comma 832 newtons. This will be the frictional force. This is one of those theorems that has a lot of application. It can be applied in many situations, so I really recommend and advise you to do as many problems as possible that require you to apply the work-energy theorem. It's quite a simple theorem. What it says is that the net work done on an object is equals to the change in the object's kinetic energy, and that alone can help you in many calculations. Okay, there are times when you are going to use the theorem to calculate a specific force, like we've just done here with question 2 of this activity, or sometimes you will be required to use the work-energy theorem to calculate a velocity. Maybe you only have the final velocity, you don't have the initial velocity, or vice versa. So this is a theorem that you need to understand, especially its mathematical implication, what it means mathematically. In terms of the definition in words, you must also know that. That's what the exam guide requires of you. You must be able to state it in words, and you must also be able to apply it in the mathematical format. That's what the last 2 bullet points of page 10 of your exam guide require you to do. Okay, that brings us to the end of today's lesson, which was lesson 2 of work, energy, and power. When we meet again, we are going to be looking at the conservative forces and non-conservative forces together with the principle of conservation of mechanical energy. If you are able to do so, please study that section or using the exam guideline together with any other learning and support material, and then come and watch the lesson so that it can make more sense to you. In the meantime, do as many problems as possible, especially problems that require you to use the work-energy theorem. This has been Butu Academy, lessons that empower. I hope that you feel empowered. We meet again on lesson 3 of work, energy, and power. In the meantime, thank you.